Welcome back to this session on buck converters. So the last session we took a look at the analysis for the buck converter when the switch of the buck converter was closed, and we came out with the results that we had over here, right? The change in the inductor current when the switch is closed. Today we are going to take a quick look at analysis for the buck converter when the switch is open. So as soon as we open the switch for the buck converter, there needs to be a path for the current in the inductor to flow, and that path is created by the diode. So over here, we have a diode. So the diode becomes forward bias. The diode turns on. Previously it was reverse bias when the switch was closed. In this case, it turns on, becomes forward bias, and then it provides a path for the inductor current to circulate. So with this scenario, and the diode being ideal, it means that the voltage across the diode, which is the same as the voltage across the filter part of this buck converter, is going to be 0. So the voltage at this node is 0. The voltage at this node, let's go back, the voltage at this node here is VO, because we are still making the assumption that the capacitor is large such that the output voltage is constant. Therefore, in this scenario, the voltage across our inductor is going to be what? 0 minus VO, which is going to be negative VO. So our inductor voltage is going to be negative VO, and using the inductor law, we have that to be equal to L di dt. We are going to follow the same procedure to try to find out what is going to be the change in the inductor current, di, for the period when the switch is open. And note, when the switch is open, we said that period is given by 1 minus d. Let's erase that. That period again is given by 1 minus d, or multiplied by the period that. So that is the period when the switch is open. Let's go ahead and erase it. So I'm going to move up slightly. And now we can write the dl, the il, the t in the form of change in il over change in t, where now we represent the change in t to be 1 minus d times t. From here, we can find the expression for the change in inductor current when the switch is open. And you are going to see that it's negative. So this change in magnitude should be the same as the change in inductor current when the switch was closed. For steady state operation, which is the assumption we made before, for steady state operation, when we add the two, or basically indirectly, the net change should be 0, which means that the change in inductor current when the switch is closed plus the change in inductor current when the switch is open should be 0, maintaining the sign of the change when the switch is open. What does it mean? It means that we can go back and equate equation 1, which is the change in inductor current when the switch is closed, and then go up here to equation 2, which is not very clear, but to equation 2, which gives us the change in inductor current when the switch is open. When we equate the two together, and it's going to be clear down here, let's go down. When we equate the two together, so that is the change in inductor current when the switch is open, and that is when the switch is closed. This sum should be equal to 0. When you solve and you simplify this expression here, you come out with that expression. Everybody is familiar with this, right? This is the same expression we had for the basic switching converter. This is telling us that the output voltage, the voltage across the load, is equal to the voltage of the source multiplied by the duty ratio D. This is the same expression we had for the basic switching converter. So here is a circuit which is giving us a constant DC voltage across our load, and we are having the same relationship as the basic switching converter which we started with. Very great. Let's take a very quick look about this equation, which we've also made a comment on already. This is telling us that the output voltage for a buck converter is always going to be less than the input voltage. Since D cannot be greater than 1, our duty ratio is always the on time over the period, right? And the on time cannot be greater than the period. So our duty ratio is 1 or always less than 1. Therefore, our output voltage is always going to be less than our input voltage for a buck converter. Very quickly, let's take a very quick look at what we have just done, and I want to show you this very quickly over here. So this is analysis we did. So for the first period, which is from 0 to the t, the switch was closed, the inductor current increased. The next period, the switch was open, the inductor current decreased, and we expect this to be in steady state. This is the change in inductor current. That is a change in inductor current from the I min to the I max. That is the change in the inductor current. So this is the change in IL. When it's going up, that is a change in IL when the switch is closed, and when it comes down, that is a change in IL when the switch is open. Some parameters we need to find. Now that we know the waveform of the inductor, the question is, how do we find I minimum during steady state operation? So we know our inductor is operating at steady state. How do we find I minimum to confirm that this inductor is actually operating in a continuous mode? How do we find I maximum? And then how do we also find I average? Okay, here I have IR, and we are going to see very shortly that the average inductor current is going to be the same as the average current. So when we find our average inductor current, then that is going to help us with the expression of the change in IL, either for when the switch is closed or open, to find the I minimum or the I maximum. On the right hand side over here, I also have the waveform plot for the inductor. So when the switch is closed, that is the voltage across the inductor, Vs minus Vo. We all saw that. And then when the switch is open, the voltage across the inductor is negative Vo. Don't forget, we could also use the average voltage across the inductor to derive the same expression which we did over here. So we could use the average voltage across the inductor to do the same thing. On the next page, I try to show you how to do that, just that. Okay, and that's a very quick one. So that is the average voltage. Okay, you can quickly do that by finding the area. So that is basically the average voltage, and when you analyze this and you simplify, now this average voltage should be equal to 0. When you go ahead and simplify, you should get the same expression or relationship between the output voltage and the input voltage. So you could use a steady state operation to obtain this same expression, and you could also use the average voltage across the inductor, which is supposed to be 0. Now current analysis. So our next focus is going to be on current analysis. How do we find the average inductor current? And then how do we go on to find the minimum inductor current? So when we go up, and the maximum inductor current. And then how do we check to make sure that this buck converter is actually operating in a continuous current mode, which means that our I min, the minimum inductor current, is not 0. Which means that the minimum inductor current is not 0. We are going to bring this session to an end, and the next session we are going to start is going to continue from here to find the current relationship, and also what are some of the things which need to be met, or the conditions which need to be met to make sure that the buck converter is operating in continuous current mode. Thank you. and make sure you watch the next video.